Good day, people. We are getting back into business. This is Max Mary with AB, and we'll continue with the topic relation and functions. So, in the previous video, we just saw types of functions and the special types of functions as a sequel. Now, we'll move on with composition of functions, which is an operation, of course, between two functions. So, let me start with a small story to understand composition of functions very well. So consider you are writing a test and it has to be evaluated. Your paper has to be in a discrete form in order to evaluate it in an impartial way or in a diligent way, right? If at all your pet of a teacher, obviously they might award you more marks, and that has to be avoided, right? So what happens is that composition of functions can be understood that way. So let's consider a student called as AB. Yeah, that's me. Okay, and I am designated with one roll number, right? Say for example 7013, right? So if at all I plug in AB in this function f, the result will be 7013. So if at all a teacher tries to manage to memorize all these roll numbers, and again anonymity goes down, right? We need another more discrete form, right? So what happens is that this roll number 7013 gets to map with another random number, say 9374. Okay, I just made up this number, right? So now it's totally a random number assigned to each and every roll number, right? So the 7014 will be like 7390 or any such random numbers. Okay, so to maintain anonymity, but that's not the case. So this 7013 is being mapped to 9374, and there exists a function. Let's assume that there exists a function g called as such. This function g takes the output of the function f, and this 7013 is the output of the values which are in the domain. A domain, let's consider that as a, right? So this is how composition of function works. You give a value that undergoes into a function, like let's take it as a factory. This is a factory of elements in the domain. This undergoes a process called as f, and the output is given in B, and this output undergoes a function g to give the final product, right? Final product. So this is how composition of function works. Okay, and then so if at all I want a values directly, like function g directly, and that's called as g composition f, right? So g, we denote that g circle f, this this thing around here is called as a circle, and we call that as g composition f, right? So which is actually g of f of x. So in order to evaluate g, you have to evaluate f first of all, and then give that as an input to g. So remember that what values will g take? The range of f will be taken with g. Okay, the function g takes the output of the function f as an input. Hope I am not playing a word jargon. Let me make this clear from the next slide. So the value x is plugged into the function f to give f of x, and this f of x is plugged into the function g to give g of f of x, called as g composition f. So this is how it goes. So together the value x is given in g composition f to give the result of the function, right? Hope I made this clear, and we'll solve the problems at the end, by the end of this video, and before that we'll see some of the properties. Some of the properties of composition of functions are as follows. Composition of functions is not always commutative. Like, you can see some functions to be commutative, but in general it's not commutative. And composition of function is always associative. Okay, So there is a proof of it, but it's beyond the scope of this video, so I am omitting it. If at all you want, you can give it in the comment box. I'll refer to a proof and let's release as another video, right? And to note an important point, wait, let me make a correction here. Yeah, so to note an important point, composition of functions will exist only if a range of a function becomes the domain of another function. Like take for example, if at all you're going for G composition f, so G compo f can be written as G of f of x, so which means that I'll take a value x and give that to f of x, right? The result will be f of x. So this becomes the range of f of x, right? This becomes the range. This set B becomes the range of f of x if at all it's 1 to 1 and on to. And you know, this f of x is now being an input for the function g, thereby giving g of f of x, right? So this f of x acts as the input of the function g. So what's the condition if at all g of f of x should be obtained? F of x has to be fully given. Like consider, let's erase this to be very clear. I'll erase this. So if at all this relation g has to be a function, all the elements of the f of x has to be mapped, right, to any other person, any other element in the codomain. So that's the case here. Hope this is clear to you. If at all it's not clear, again mention in the comment box. Yeah, so we'll solve some of the problems to make this concept a very clear one, using the given functions f of x equals 3 plus x and g of x equals x minus, and f compo g and g compo f. And so let's go with the solution. So let's find f compo g first. So f compo g is given as f of g of x, and we know what is g of x, right? It's x minus 4. So let's just plug in x minus 4 here, and we know that f of x is 3x plus 3, or 3 plus x, never mind, right? So f of x is 3 plus x. So instead of, like, if at all it's x here, you'll put x here. If at all it's x minus 4, instead of this x you will mark x minus 4, right? So this becomes 3 plus, instead of x you have x minus 4, yeah, and thereby solving it you have 3 plus x negative 4 plus 3 and negative 4 gives you negative 1. So the function f compo g is x minus 1 or x negative 1. So yeah, that's the problem. And what about g compo f? So we already know that g compo f means g of f of x. So g of, what do you have as f of x? You have 3 plus x here, so let me plug this in. And g of 3 plus x, we know that whenever you have x here, you'll substitute x here. If at all you have y, you'll put y minus 4. Like now you have 3 plus x, so it becomes 3 plus x negative 4, and it becomes 3 plus x minus 1, I mean minus 4, and this becomes x and negative 1. See here, you have now an example for f compo g equals g compo f here, but it's not the case always, as I said in the previous slide. So let's go with another problem if at all this statement becomes false. And now here, yes it is. So we'll have another problem to be solved. So it's x minus 6 as f of x and x square as g of x. So let's try to solve this problem, right? So let's go on with the solution. Let's find f of g first. So it's basically f of g of x, right? And f of, let's plug in g of x first. So it's x square, and see, in the place of x you have x here. So now in the place of x square you put x square. So f of x square means x square minus 6. So f of g becomes this. And no more simplifications can be done, so let me move on with g compo f. So g compo f means g of f of x, and that means g of f of x is x minus 6, right? And yes, Now instead of x you put x square, so if at all it's x minus 6, you put x minus 6 the whole square, which is basically x square minus 12x plus 36. If at all you know the identity a minus b the whole square, you'll be able to solve this. And note that g compo f and f compo g are not same here, so it's not always commutative, and hence the proof. And let's verify the associativity and then we'll wind up the video. I'm not taking more long, I guess. Let's see. Okay, so composition, I mean associativity of the composition of function goes like this: f compo g compo h will be equal to f compo g compo h. Yep, let's go with left hand side. So what do you mean by f compo g compo h? See, f compo g compo h, like f compo g compo h means the output of g compo h goes as the input for f, right? So let's find what's g compo h first. So g compo h is g of h of x, and g of h of x is x square, and this x square goes as the input for g of x, so it's 3x square plus 1. Like instead of x you have x here, so instead of x square you put x square, that's it. So this is g compo h, and this g compo h will be substituted here, right? For simplicity I'll do like this. So f compo g compo h can be written as f of g compo h. We already know that g compo h is 3x square plus 1, and you know instead of f of x you have x minus 1, so f of 3x square plus 1 goes like 3x square plus 1 negative 1, and that gives you 3x square. So this is f compo g compo h. Okay, let's keep this aside, and while then we go for what does RHS tells. So f compo g compo h, what does this mean? First of all, let's find what is f compo g, and h of x will be the input for f compo g. So we have h of x to be x square, and let's find what is f compo g. So f of g of x, so it's f of g of x is 3x plus 1, and minding this in f of x, I mean plugging this in f of x, that gives you 3x plus 1 minus 1, and that's 3x. So f compo g is 3x, and yeah, f compo g of compo h means f compo g compo h means f compo g of h of x, right? So f compo g of h of x is x square, so you plug this x square in f compo g. So like f compo g is 3x, instead of x you have x square, so plug in x square instead of x, so 3x square. So look, that associativity is verified. LHS equals RHS, hence the proof.